Thanks again for joining us today. I'd like to turn it over to Mr. John Stanislaw, who's going to be presenting for us this afternoon.
All right, thank you, Heather. Welcome, everybody. Hope you're all doing well. I see we've got a couple people from around the world here, besides the United States, which is awesome. And today we're going to take some time to talk about aircraft rescue firefighting. And specifically, we're going to get into some tactics, and we're going to talk about the use of encapsulator agents in this field. So I've been a firefighter for 36 years now. ARFF certified. I've been with HCT now for over 4 years, and I really have a lot of passion for this because aircraft rescue firefighting is where when we have to go, we have to go, and we're expected to save a lot of lives with a few people and a couple of trucks. And it's when you think about it, our small indexed airports are, index A airports, there may be one person in a truck, and they're expected to save up to hundreds of lives on an aircraft. So we're really going to get into it today and talk about the benefits of encapsulator agents and what they can do for us. So our company, Hazard Control Technologies, has been around since 1997. Based in Fayetteville, Georgia, we're a U.S. owned and operated ISO 9001 certified company. We're on 6 continents, and hopefully someday we'll be in Antarctica. And when it comes to lithium-ion batteries, we have 17 years of testing around the world related to lithium-ion battery fires. But beyond that, we're a multi-class firefighting agent. The future is now. When we talk about aviation today, there are so many new things that we've thought, oh, that'll be someday. Electric aircraft, hydrogen-fueled aircraft. We talk about uh, exotic metals, airplanes, right? Weight is waste in our aviation, right? The more we can reduce weight, the more we can save on fuel. So lightweight titanium, aluminum, magnesiums, right? Metals that burn. Carbon composites, while carbon fiber doesn't burn, we know that the resins and glues in them do. And they form a big challenge for us with dealing with them. And we're starting to see, the face of net zero. A lot of airports now are saying by 2030, 2035, they're going to be carbon neutral on the airport. That means electric tugs, electric pushback vehicles, electric fueling vehicles, right? Who thought it was a good idea to put a couple thousand gallons of jet fuel on top of a giant lithium-ion battery? So these are challenges we're expected to face. We're expected to come up with solutions to this, right? There are airports that are putting battery energy storage systems on site to store energy to recharge those tugs and pushback vehicles. So a lot of these things are here, they're now, and electric aircraft. Um, and I want to show you something. So that aircraft is not vaporware, that is not AI, that's an Archer Midnight. Archer has been selected as the official air taxi provider for the 2028 Olympics. They spent $128 million to buy the Hawthorne Airport. Not part of the airport, not to lease the airport, they bought the entire airport. And their plan is to use those Midnight aircraft, which will have about 6 people on board, a pilot and passengers, and shuttle them around venues in the LA basin during the Olympics, and also to shuttle people to and from airports. This is real. These aircraft are out here, they're coming, and that aircraft is powered with 6 lithium-ion batteries, which have pretty much the total power capacity of a Rivian. So imagine, a flying Rivian crashing somewhere and catching fire. And we're expected to address that. Personal eVTOL aircraft. These things are coming. I saw that some of you are from municipal fire departments that maybe have a non-indexed airport in your jurisdiction. These things are flying. I have actually seen a demonstration of an aircraft called the Black Fly. It's a one-person aircraft. These are in production now. Again, large capacity lithium-ion batteries. They will be crashing in your communities. They've already had crashes with these aircraft. Ground sport equipment. Okay, think about the battery energy density needed to push back a 787, an A380. Okay, these large pushback tugs, in some cases, are packing the equivalent of 2 to 3 Tesla Cybertruck batteries in them. And we're also seeing a change from using a tow bar to a nose wheel capture. So this is a nose wheel capture tug, right? Where it literally goes around the nose wheel and lifts it ever so slightly off the ground and tows the aircraft. The problem is it puts it much closer under the nose of the aircraft. It positions these batteries generally underneath the forward doors. If this thing goes into thermal runaway and starts to burn, it's going to be directly impinging on the open nose wheel well, and it's going to prohibit the use of the forward slides, right? So if this thing is burning under that jet and there's a couple of hundred people on it, we need to be able to address that. And we need to be able to address it quickly. And in our opinion, we need to be able to address it with turrets. PEDs, man, I go to ARFF conferences and I talk to people and I ask them, are you having fires in your gates, in your terminal areas from personal electronic devices? And the universal answer is yes. Cell phones are burning, laptops are burning, these new roller bags that have the battery charger bank built into them. My son did Vex Robotics for a couple years in high school. When they would fly to tournaments, they would pack the robot up in a box and it would go in the cargo hold, and they would take the large lithium-ion batteries on board the aircraft with them in their carry-on bags. So these are issues that we have to face, and it's not just in the cabin or in the cargo hold, it's also in your terminals. What are you doing in your terminals to deal with lithium-ion battery fires? This is here again, this is here now. This is not a thought experiment. So in 2025, UL Standards and Engagement published lithium-ion battery, and they looked at batteries on aircraft and in flight. And it's a driving concern. You know, we're getting more and more of these devices on aircraft. Even pilots are using them. They're flying with tablets, with ForeFlight and other flight programming stuff. We have the flight attendants are using tablets when you buy beverages, right? So they're using a lithium-ion tablet. So these things are really dangerous because you're in an enclosed environment, right? So when we start to have a thermal runaway event, all that smoke and toxic gas is in the cabin with everybody.
Hey, John.
So, yes.
Sorry to interrupt, but the audio cut out a bit.
Oh, you got me here
So on the low side.
on the low side.
Yeah.
How about this? Any better? Put my microphone closer.
Yeah, much better. Thank you.
Okay, I'm going to do that. So in 2023, there was an average of 2 incidents a week on aircraft. Now think about that, 2 a week. Overall incidents were up 15%. 18% caused a major disruption, declaring an emergency, having to land somewhere they didn't intend to. 89% occurred on board aircraft in flight, and 11% occurred on the ground. The number one cause, we know, vapes and e-cigarettes, right? 28% of the cause, even though only 10% of the passengers carry them. And then, of course, smartphones, laptops, headphones, tablets, power banks. When I flew last month going down to DFW, pretty much everybody was wearing either headphones or earbuds. Again, all lithium-ion battery, right? These are all on these aircraft. And hey, people, right? The people factor. 38% of people put lithium-ion powered batteries and devices in checked luggage. They're not supposed to, but they do. And when the gate check, and you've all been there, they ask, hey, please make sure you remove the devices from your bag before you give it to the gate agent. How many people have you watched actually go through their bag and do that? And when we have a fire on board, what is our most common type of extinguisher? It's either a halon or halotron or now halotron BRX extinguisher, which are ineffective on lithium-ion battery fires. Yes, they will give you an initial knockdown, but it will not stop the thermal runaway process and the battery will go back into a flaming state. So what do? We give flight attendants oven mitts and bags and tell them to put on a smoke hood and grab a very angry laptop and try to shove it in a bag and pour a coffee pot into it or bottles of water. That's not a solution. We need something better than that. Boy, if you're in the technology, the change, right? Obviously, the amount of fuel aircraft carry, especially getting a larger wide body aircraft. And again, we talked about titanium, magnesium. Some of these aircraft have up to 18% titanium by weight. Titanium, as we know, is a combustible metal. You stamp it into large, flat pressings, wide surface area, you make more of the metal available to burn. You can get very violent fires. So if you look at some of the new Airbus aircraft, up to 50% of the aircraft is carbon fiber. And again, when you look at the Japan Airlines collision, back in that would have been 24, when the Airbus hit the Japanese Coast Guard plane, that aircraft burned for hours. It wasn't a fuel fire, it was fire that got into the carbon composite fuselage. Now we're learning that as carbon fiber burns, it actually forms an insulating char. That's why we wear carbon fiber firefighting hoods, right? It's sacrificial. It forms a char that protects us, insulates us from heat. Well, that traps heat in the fuselage and the airframe structure and actually causes a much hotter, more difficult to extinguish fire. And lithium-ion batteries. We talk about hybrid and electric aircraft, but we also know the Boeing 787 uses lithium-ion batteries on board the aircraft. The F-35 fighter has a pair of lithium-ion batteries in its weapons bays. Again, who thought that was a great idea? But we're getting these batteries, and whether they're the primary source of propulsion for the aircraft or are used as an energy storage device, they're on. So the vicious cycle of foam. So one of the things that we talk about in our industry is evolution, innovation, right? I gave a presentation a few years ago talking about when the U.S. Army Air Corps in World War II, when they rolled the B-29 out, the Super Fortress, the mechanical foam systems they had on their fire trucks could produce about 40 gallons a minute of foam. The Super Fortress created such a huge fire problem that the Army Air Corps eventually developed large carbon dioxide trucks that would carry thousands of pounds of CO2 that they'd use to extinguish gasoline fires. It's very innovative thinking. And that's what we're talking about. Science proved to us that AFFF was dangerous. We had the toxic PFASs and PFOSs. It caused a cancer risk to us, and it caused an environmental risk to our communities. So industry pushed to replace it, and we came up with synthetic film forming foam. Well, synthetic fluorine-free foam, I'm sorry. There's so many F's in this world. Synthetic fluorine-free foam. Well, when we went to synthetic fluorine foam, we went backwards about 60 years. We went back to basically what AFFF was created to replace, which is a protein type foam, right? You mix a liquid with water, cause aeration, right? We know we need air aspirating tubes. Air aspirating tubes are recommended for use with fluorine-free foam. And we went back to creating a mechanical bubble blanket that had to be maintained to mechanically separate the fuel from the oxygen. And that meant we had to apply it slowly and, of course, indirectly, where with AFFF we could apply with a standard nozzle and a direct attack, bank, roll, rain, right? And we know that for right now in the United States, the FAA favors foam as a primary agent. Even though many of you know, as you've gone to these training sessions and you've used it yourself in training, it's not as efficient as we would like. And so we know that right now, if we only have water, Purple K, and fluorine-free foam, we're not really prepared and equipped for modern aviation hazards, right? And that's what we're going to talk about. All right. Oops. I gotta go back one. All right. So let's get to encapsulator technology, and I'm going to turn this sound down. So really, when we talk about encapsulator technology, conforming to NFPA 18A Section 7.7, what we're talking about is molecular chemical firefighting. So you have a polar head that loves water, and a non-polar tail that hates water, wants everything to be away from water. So when you mix an encapsulator agent into a water stream, what happens is those polar heads go next to each other, and the nonpolar tails go inside, and you form what's called a spherical micelle. So those polar heads are next to the water where they're happy, and the nonpolar tails are in away from it where they feel safe. Once they're discharged from the nozzle, something interesting happens. On every droplet of water, the spherical micelles on the surface break apart, and those polar heads snuggle up against that water droplet, and those nonpolar tails radiate outward. But inside the droplet, there are millions and millions and millions of those spherical micelles. So if that water droplet you see was the size of the Earth, each of those micelles was about the size of a pea. And because those polar heads have the same charge, they repel each other. So those spherical micelles bounce around and race around inside that water droplet. They come up against the surface. And so when this droplet encounters a hydrocarbon, say jet fuel or aviation gasoline, it pushes that hydrocarbon inside the droplet, and it breaks it down to the individual molecules. And each molecule is chemically cocooned, much like Pac-Man eating the little white dots in the game. Each fuel molecule is chemically cocooned. At that point, it will never burn again. It will not come out of suspension. Even better, it will begin to bioremediate on its own. So we make those little um, molecules more amenable to be eaten by the microbes in the environment. But what's really cool is this thing wants to encapsulate any carbon or hydrocarbon. So the flammable electrolytes in a lithium-ion battery, that's a hydrocarbon. Hydrogen gas, so hydrogen-powered aircraft use fuel cells. You have a liquefied hydrogen leak, creating a gas cloud. You can spray this into the gas cloud and actually knock the cloud out of the sky. Encapsulate it, and it will not burn. It's an amazing agent. It also has an amazing ability to absorb heat, up to several hundred times better than water. So we talk about those carbon fiber aircraft fuselages and things like that, where we've got a lot of heat and we need to get that heat out of that fire. And it also strips the toxins from the air. So your hydrogen cyanide, hydrogen fluoride, um, carbon monoxide, all of these things, it's knocking them out of the sky. And when we talk about interior aircraft firefighting with the synthetics inside the aircraft, and the toxins that are released, right? The vast majority of people that die trapped in an aircraft fuselage in an aircraft crash died from smoke inhalation, not from fire, not from traumatic injuries. They are trapped in their seats and they die of smoke inhalation. NFPA 18A, Section 7.7 in 2022, this standard was introduced to the NFPA. It's a standard on water additives for fire control vapor mitigation. And it talks about the testing criteria needed to prove that an encapsulating agent can meet NFPA 18A standards. In 2023, in AC 150 5210 6 Echo, the FAA included encapsulator agents in the circular for aircraft fire extinguishing agents. And this allows us to carry it on indexed apparatus at airports. Now, keep in mind, for all of my municipal firefighters here that protect non-indexed airports, meaning you don't have regularly scheduled passenger service that meets the FAA requirements to have on-site crash fire rescue, you can use this. I have a number of airports. I'm in the Pacific Northwest. I have a number of municipal airports where the fire departments that are protecting them are using this as their agent of choice. We have this all over the world. So if you have a small general aviation airport, and you're concerned about flammable liquid fires or electric aircraft fires, you can carry this on your apparatus and use it. So, but the advisory circular inclusion allows us to include this agent not as a replacement for, in addition to the primary agents we're required to carry. All right, we're starting getting the meat and potatoes now. We talk about foam. Foam is a mechanical construct, right? So we all know we take a foam concentrate, we mix it with water, whether through it's an injection system, around the pump system, a ductor, batch mix, a pro pack, something like that, and we discharge it. And our goal is to make a thick, homogeneous bubble blanket. We want that thick, homogeneous bubble blanket to separate the fuel from the oxygen, and we get some cooling effect from it. Now, we need to make sure we maintain that blanket. We don't want breaks in the blanket. Anywhere we get breaks, we're going to have vapors released and we're going to have fire, right? So we have to maintain that blanket. As we walk through it, as we work in it, we disrupt it. If there's heavy rain, if there's winds, it disrupts it. We have heat that's burning back against it. It disrupts it. Okay, and we have to keep reapplying. And again, we have to apply it gently. If we plunge, we're going to pick up fuel, right? That was one of the benefits that PFASs gave us with AFFF, right? That's why we had subsurface injection for fuel tanks, right? You could get it into the fuel, it would prevent the foam bubbles from wicking the fuel up and burning. We anymore now, if we have fuel wick up, you're going to get foam burning. You're going to see the ghosting. You're going to see tunneling. You're going to see things like that. When we talk about encapsular agents, again, now we're at a chemical molecular level. We don't need to make a blanket. In fact, you don't want to air aspirate encapsular agents. What you want to do is you want to aggressively mix the solution, generally a 3% solution for hydrocarbon fires or batteries. You want to aggressively mix the solution with the fuel and chemically encapsulate it. What's really cool about this is then we're not limited to two-dimensional fires. That encapsulation can occur in the air. So we can deal with pressurized liquid and gas fires. We can deal with three-dimensional fires, engine nacelle fires, flowing fuel fires. We can deal with all of that. In addition to complex Class A, including deep-seated Class A, um, Class C fires, encapsulator agents that meet the Section 77 test have the same conductivity as water, which means when we use something like a 30-degree fog pattern at the appropriate standoff distance, we can fight energized electrical equipment fires. And again, those combustible metals, those Class D fires, that magnesium, that titanium that we see on aircraft, and the lithium-ion batteries. So this is an example of how this works. So this is the Section 77 spherical micelle stability test. So what we're going to do is we're going to pour a gallon of gasoline, so straight up gasoline into a pan. We're going to add 16 ounces of an encapsulator agent. So 1 to 8, and then we're going to add 5 gallons of water with agitation. So that's our 1 to 8 to 40 mix. And again, you're going to see, unlike a gentle foam application, he's going to very aggressively mix everything together. This is the goal that we're shooting for, right? We want to get that good agitation. So those spherical micelles now are encapsulating the gasoline molecules, locking them up and making them unable to burn. So you wait 2 minutes for this test, you pass a torch over it. You cannot have any ignition, any signs of fire, no flashes or ghosting or anything like that. And then, to prove that we have encapsulated the fuel, he is going to take a bucket. And again, this is not CGI or cute editing tricks. He's going to take a bucket of that encapsulated gasoline, and he's going to use it to extinguish the burning tires in the background. So that is chemical molecular encapsulation. That is the fundamental way this agent works, right? So let's compare agents, foam, water, and encapsulating agents like F500, all right? We talk about reactive versus proactive, right? Foam and water tend to be reactive things, right? We have a fire, we have an emergency, we have something going on, we're using it again in a reactive mode. We talked about a hydrogen leak, right? You have that hydrogen fuel cell powered regional commuter aircraft that's sitting at the gate. The liquid hydrogen truck comes up to fuel it. There's a failure, and now you have a large cloud of hydrogen spreading across the ramp looking for an ignition source. You can actually come up and spray into the cloud and molecularly encapsulate that hydrogen and knock it out of the sky. It's pretty impressive what this agent can do. We talk about foam. Really, it's only for flammable liquids. Yes, we can use it for Class A fires because it is 97% water, but primarily it's a flammable liquid, a two-dimensional, a flat spill fire. Water, well, water is water. It's great, but when we go to our, flammable liquids, it's not effective, right? Combustible liquids, diesel and things like that, sure, with a fog pattern, but it's really limited. And on our gases and stuff, all we're doing is trying to disperse the cloud, not encapsulating it. Um, Water, we need lots of it, right? And especially when we're on the airport, water is a precious commodity. There's not a fire hydrant every 500 feet like in the municipal firefighting. We have to be careful about our water supply. We can't mitigate toxic environments, right? Foam. We're finding out with fluorine-free foams, we're needing up to 1.5 to 3 times more than we normally did with AFFF. And again, that slow application. Um, we know that our job in ARFF is to position our apparatus to separate the fire from the passengers, right? We're there to separate the fire from the slides to create egress pathways. If you're an Index A airport and you're one person on a rig, that is really the only thing you can do. You roll up to the aircraft, take a position at the nose, and push the fire away from the slides, right? So we want to do that quickly. AFFF gave us the ability to roll up, aim down into it, and just sweep it away. Now we're rolling on blankets. We're raining, okay? With an encapsulator agent, we can go back to that aggressive direct attack again. So, everybody in ARFF recognizes this prop. We've all been on it. It's a three-dimensional nacelle fire, right? And we show this video and we say to people, how do you address this? And they go, well, hydrochem, right? I'm going to roll up, I'm going to use a hydrochem nozzle, I'm going to get the cooling from my foam, I'm going to have my dry chem inside, and we're going to do twin agent attack to extinguish it. So this testing done by the Italian Navy. The Italian Navy has replaced all of their AFFF with F500. And this is some of the testing they did. And so this is a 3% solution with a 95-gallon hand line using salt water, because again, this is for the Navy. So this is a saltwater attack with a 3% solution. They're doing two things. They're cooling the steel below the fuel's ignition temperature, and they're encapsulating the falling fuel. So we're attacking multiple sides of the fire tetrahedron. We're taking away the fuel through encapsulation, we're cooling the steel to reduce it below the ignition temperature, and we're interrupting the chemical chain reaction, right? Very powerful what we can do with this agent. So we talked about in the terminal. This is testing done by the Port Authority of New York and New Jersey. This is an e-scooter battery. And they're going to induce a thermal runaway with a propane torch. And you'll notice the battery is in a blast cage, right? So a battery pack is made of modules, and modules are made of cells. In this case, 18650s, which are like a fat AA battery. So they have concerns on the trains, in the airports, in the gate areas, right? All these places on ferries where people have e-devices. And so they said, hey, who's got agents that can deal with this? And so we answered the call, and they're going to fight this 3 kilowatt-hour battery with one of our 2.5-gallon extinguishers. So you see the thermal runaways induced. We're going to start seeing individual cells take off and pop. And they're going to attack it with a 2.5-gallon extinguisher with a water mist nozzle. Now, one of the things I want you to see is application technique. Whether you use an encapsulator agent or you use water, whenever you deal with a lithium-ion battery fire, you have to keep the nozzle moving. Wherever you see the flames, you have to apply agent, right? You can't just hold still. So you're going to see this firefighter, he's going to start hitting it from one side, and he's going to aggressively work his way around the battery, fighting the fire. So he gets one side, looks pretty good. He's going to come around the other side, he still has some flaming. Again. So again, when we have lithium-ion battery fires, the reason these are so difficult to extinguish is because of the flammable electrolyte and the stranded energy. The stranded energy is our reignition source, and the flammable electrolytes are fuel. If we can encapsulate that flammable electrolyte, regardless of how much stranded energy is in there, it won't burn. So by the way, he used about a half an extinguisher to put that out. So about 1.5 gallons, and then they went around and did a little more mop up on it. But that battery is extinguished, and it did not reignite. So this, anybody that's ever been to the city of New York and had the opportunity to go through the tunnels knows the Port Authority runs little tunnel emergency vehicles. They're a combination tow truck, fire truck, push truck, and they carry a 50-gallon, basically compressed air foam system on them, twinned with a Purple K system. And so this is using one of their tunnel trucks on a hybrid. So in this case, the battery pack is under the floor in the back seat. So they induced a thermal runaway, and they're attacking it with a 95-gallon-a-minute stream from the tunnel truck nozzle. And you can see they got a really awesome knockdown on the fire and extinguishment. So what's really great, we talk about agent conservation. The knockdown of this agent on our Class A fires, on our Class B fires and stuff, it's pretty powerful. So they extinguished that entire vehicle with under 50 gallons. So one of the things when we talk about NFPA is the NFPA equivalency clause, okay? And if you look at any NFPA code in the beginning, they'll all say the same thing. Nothing in the code is intended to prevent the use of systems, methods, or devices of equivalent or superior quality, strength, fire resistance, or safety, provided they are approved by the AHJ, right? So what does that mean? That means if you would like to put F500 fire extinguishers in your terminal, in addition to your existing ABC dry chemicals, not to replace them, but to supplement them with the appropriate signage saying there for use on e-device fires, you're permitted to do that as long as the ASJ approves it. And the same thing comes to when we talk about ARFF vehicles, right? So long as you meet the FAA requirements for a primary agent, the appropriate amount, the ability to discharge it, and all the systems, there's nothing that is preventing you from speccing a vehicle with a second agent cell and speccing a dual agent system. So I have personally spoken to engineers from E1, Oshkosh, and Rosenbauer. All three of them offer, as a standard option, the ability to go with a dual agent foam system with two tanks with a selector switch in the cab, right? So we talked about that giant pushback tug burning under the nose of that A380 or 787. You can roll up and go, hey, that's an electric tug that's on fire. It's impinging on the airplane. It's preventing the use of slides. You can flip that to your second tank and attack that with your turret with an encapsulator agent. Fire spreads and you have a fuel fire on the ground, you still have the ability to flip the switch the other way, right? So you can spec these. And there are airports right now in the United States that are looking at speccing ARFF vehicles with two tanks and a dual system. So applying it, this is what I like to call our continuum of extinguishment, right? We talk about gallons a minute and the ability to sustain an attack. Now, generally, we've found in testing over those 18 years of testing and real world performance on actual fires that roughly 1 to 2 gallons per minute per kilowatt hour is what's needed to deal with a battery fire, right? So when we have our small e-devices, our laptops, our little battery power banks, our vape pens, things like that, handheld extinguishers, our small wheeled units, self-adducting nozzles like our TKO nozzle or a Pro Pack, those work very well on them. Now, parking garages. This is a huge issue. This is a huge issue outside of aviation with electric vehicles, right? So we have fires, about 50 to 56% of all electric vehicle fires start from parking or charging, right? And not necessarily on a charger, just sitting in a parking spot and going into flames, right? And a lot of agencies are looking at these low profile initial attack rigs for airport parking garages. Um, These are great. You build them, so they're under 7 feet tall. They can get in there and they can start an initial attack with, the 3 to 500 gallons of water and F500 they have on board while you're working on setting up a sustained water supply. So we start to get into passenger vehicles, e-buses, aircraft, and large electric ground support equipment. Now we're starting to get into needing, several minutes of application and starting to get upwards towards, 150 to 250 gallons per minute. So that's where we're talking larger tanks on apparatus. Some airports are fortunate enough to have structural apparatus as part of their ARFF contingent. You can fill the foam cell on the structural apparatus with this and use it for those larger hazards. And then we get into things like parking structures, charging stations, large, Connex box size battery energy storage systems. This is where we need a lot of agent for a long time. So we have trailers. Now, this is our special agent trailer. This has our water-driven proportioner on the back. It's a pretty amazing unit. We're going to talk about it a little more in a minute. But the thing to know is that all of our trailers are also available as skid units. So in this case, this has 500 gallons of F500 on board. You can have it as a trailer, or you can put it on the back of a flatbed of like a Super Duty pickup and have this staffed when needed. So you can have somebody jump off the pumper, jump into the truck that has this on the back and bring it to the scene. And all you need to do is supply water to it. So the trailer, it's a pretty amazing unit. It's got a 6-inch inlet. It can do up to 1,500 gallons a minute at 3%. It's got 550 gallons of F500 on board. It's got a 50-gallon minute refill transfer pump. So if you have that vehicle that you want to transfer it to, or if you're running low on agent, you can bring totes to it and use that transfer pump to refill the trailer. It's got 360 LED lighting, and it comes equipped with that nozzle you see there, a pair of blitz fires, hose, everything. So this is an amazing unit. We see more and more agencies going for things like this, and again, some of them are doing them as trailers, and others would rather use them as a skid unit mounted on a vehicle. All right, let's talk tactics. Let's talk firefighting, thing we're all here for. So remember I said we're not blanketing. So if you look at that F500 solution that's on the ground, that's a 3% solution. That is as bubbly as this stuff gets. It really looks like 2% milk when it's laying on the ground. Now, the smaller the droplet size, so we're using a fog nozzle here, the more effective it is. You want to make sure that you aggressively fight the fire. What do I mean by that? You're going to watch when they come in here. They're going to hit this straight on like they were using water. An aggressive sweeping attack. That's a 7-second knockdown. This was done. This is a nuclear power plant fire brigade. Obviously, transformer fires are a big thing for them. So that was a 100 GPM nozzle. They use under a half a gallon of concentrate, and the fire is out. So that is the knockdown, and that's the application of this stuff. Aggressively fight the fire. Boy, Class D metals. I think everybody has had that experience. You're fighting the car fire, the stream hits the magnesium steering column, and all of a sudden, big bada boom. Well, if it didn't work once, let's try it twice. No, it didn't try work. Let's try it again. Yeah, magnesium. When we talk about encapsulator agents, we have the ability to cool burning metals faster than they can crack the water into the hydrogen and oxygen. How do we do that? Well, we gently rain a 3% solution down. So when we talk about fighting combustible metal fires with encapsulator agents like F500, patience, right? So what these firefighters are doing are they're gently applying a fog stream. So as long as we have white hot, we're above that temperature where water will crack into hydrogen and oxygen. So we're gently going to cool. And this may take several minutes depending on how much weight and mass of metal there is. Now, once we see that white hot turn to more of a yellow, orange, and then into that deeper red, now we can go more direct attack. We can get closer. We can narrow our stream down. This is a large piece of titanium, by the way. So we're gently showering it, you know? And now this firefighter that was just burning at 5,000 degrees is going to take his glove off. He's going to pick up that piece of titanium. He's going to pass it around to the other firefighters to feel. That is the effectiveness of this agent on things like combustible metals. No giant explosion, no excitement, just a nice, rapid, slow cooling of it and getting your fire extinguished. All right, lithium-ion batteries. These are two batteries out of a Porsche that are in this prop here. Now, we're going to talk about you want to use small droplets. The finer a fog you can get. Ultra high pressure is an amazing delivery tool for encapsulated agents like F500. But in this case, they're going to use a fog nozzle. We're not going to straight stream it. And we're doing that for a couple reasons. One, we want to get that large surface area coverage. But two, we want to knock down all those explosive vapors and toxic gases. So as you watch these firefighters fight this fire, I want you to keep your eye on the smoke above the battery, right? And you're also going to see they're aggressively going to move around the battery while they fight the fire. So watch that smoke above the battery as they start to hit it. So where we had the black smoke and the toxic gas, now we all have warm white water vapor. And they're going to very methodically move around those two batteries, applying that fog pattern and working on encapsulating the flammable electrolytes. Now, one of the questions people often ask is, well, if this is a liquid-based agent, how do you get inside the battery? Well, that's easy. See all the holes the battery is burning in itself? So the battery will vent either through natural vents or it'll burn holes in the pack. And that's why we tell you wherever you see the flames is where you want to apply the agent. So they're going to move around, they're going to find where those flames are, and they're going to apply the agent there. And it's going to work its way into the battery pack and ultimately cool the neighboring cells so they don't go into thermal runaway. They're going to encapsulate the exposed flammable electrolyte and prevent the battery from reigniting. And again, you see that nice methodical fog attack around the battery. The fire is extinguished. The battery, again, did not reignite. All right, so we're getting towards the end here, and we talk about comparisons, right? So foam has to comply with NFPA 11, which is the standard for foam. Foam adds environmental contamination, right? Foam, even the new fluorine-free foams, still have stuff that you don't want in the environment. Really only addresses two-dimensional flammable liquid fires. When we talk about three-dimensional fires, in NFPA 11, the standard on foam, NFPA states foam is not the appropriate agent for three-dimensional fires. And really, most adequate Class B foams still contain some type of PFAS, right? Whereas you look at F500, we comply with the NFPA 18A standard for encapsulator agents. We encapsulate these things. We help prevent environmental disasters. And F500 EA is actually approved by the EPA as a surface washing agent, right? It makes these hazards more amenable to bioremediation in the environment. We mitigate multiple parts of the fire tetrahedron, right? The flammability, explosivity. We knock those toxins out of the sky and encapsulate them. NFPA 18A confirms that these agents are effective on three-dimensional fires, and the product is fluorine-free, biodegradable, and non-corrosive. Believe it or not, it actually meets the USDA requirements to be a food additive, even though we don't recommend you drink it or put it on your salad. So we talked about these risks, right, over the last 45 minutes. We talked about the aircraft and the changes in them. We talked about the hazards at the gate, in the hangar during maintenance, in our parking garages, out on the runway, on the tarmac with our pushbacks and our tugs and things like that, in the terminal, and at the TSA gate where people will bring everything and anything through, right, which brings those hazards with them. So I want to thank you guys for attending. We're going to get into Q&A here in a minute, but we just wanted to let you know that our next upcoming webinars are going to include disaster preparation, EV firefighting tactics. Highly recommend all of these are great information. And then that battery energy storage system. Like I said earlier, we're seeing large 40-foot shipping container size BESSs going on airports to provide charging to electric ground support equipment. So this hazard is coming to your home. So thank you. There's our phone number, our email, and yeah, let's take the last 15 minutes to get into some questions. I see there's a couple of them. Let's see, chat, quick chat. There we go. All right. Let's see. Any questions? Throw them out there. Um, Anybody? I am scrolling through the chat here. So James, I see on there straight misinformation. Um, so I'd love to hear what you have to say. And one of the great things about our company is we have, like I said, 18 years of testing, specifically lithium-ion batteries, and then, of course, all of the years on flammable liquids and things like that. We're in use in multiple countries. Like I said, we are the agent of choice for the Italian Navy. Our agent has U.S. military NSN numbers for our 5-gallon buckets and 55-gallon drums. We have our chronology of lithium-ion battery testing, which we can send to all of you, safety data sheets, videos. And the other thing is we would love to come to you and show you what we can do. Do we recommend use on fuel spills? Yes. What's great about it is you can encapsulate a spill, much like that lockup test. So think of that as a spill, right? So you've got gasoline on the ground. You're going to agitate it with that 3% solution. You're going to lock it up. Generally, you want a roughly 5 gallons of a 3% solution per 1 gallon of hydrocarbon. So if I have 10 gallons of gasoline on the ground, I'm going to want to agitate it with about 50 gallons of a 3% solution. That will lock it up and then it will not burn. I saw something about temperatures. So it needs to be, the concentrate needs to be freeze protected, right? So you don't want it to freeze generally, between 32 degrees on the low end, 120 degrees on the high when you're storing the concentrate. When it's mixed in something, though, so say an extinguisher, batch mixed in a tank or in one of our wheeled units, you can freeze protect it with food grade propylene glycol. And we've tested it on fire. We've passed the 18A spherical micelle stability test with a 50-50 solution of water and food grade propylene glycol. And at that mixture, we can freeze protect it to minus 31 degrees Fahrenheit. And if you don't need to go that far, then you can ration it, and we have a form on rationing it. Let's see. Is there anything it doesn't react well with? Yeah, we actually did some testing with potassium metal, and we know, potassium, you get it in water, it tends to like to explode. We threw some in a encapsulation solution and it delayed the explosion. So instead of exploding immediately, it waited a few minutes and then it blew up. So there are certain exotic hazards that we don't recommend using it on. And if you have an exotic hazard, please contact us. We probably have already done testing. If not, we'd love to come do testing with you. Yeah, does cool the battery. F-35 takes about 30 to 45 minutes to get out of the aircraft. Yes, it does. And so you can apply it directly to the pack, and that heat absorbing will basically draw the heat out. Think of it like a very powerful heat sink. So we've done tests where we've taken a sheet of metal, held a torch to one side of the metal, maybe 3/8 of an inch thick, and we're able to put our hand on the other side as long as it's being cooled. Radioactive materials, we've never tried it. If you have a nuclear reactor and you'd like to invite us to come check it out, we would absolutely love to come. That's the other thing. If any of you would like, if you have something and you're curious about the effectiveness of F500, we would love to come out and test with you. That's where most of our testing has come from, honestly, is people reaching out to us. Yeah, similar to cold fire. Different. It's a different agent. In our opinion, it's a better agent with testing. So yeah, like Ken said, as far as we understand, cold fire has not been able to pass the spherical micelle stability test. Radar systems. Okay, so same corrosivity as water, right? So it's got a pH of 7. It's passed, corrosivity tests. And so I would say if you're okay with putting water on a radar array or electronics, if you're okay with putting water on it, then you could just understand it is 97% water. Um, how often does it need to apply for fuel spills? Generally, once you have complete encapsulation, it's one and done. And then it will break down in 30 days in the environment. So the firefighter street method that I teach when I train folks on this is apply it, agitate it, mix it, take your combustible gas meter, go to your LEL, correct your LEL for the hazard you have, kerosene, gasoline, whatever that hazard is, correct your LEL meter and run your probe over the spill. As long as you're getting 0 LEL across the surface of the spill, you've accomplished your encapsulation. And then again, one and done. Um, how can we help get the FAA more open to F500? Great question. What we can do is ask for real world testing. So what do we mean by that? We would like to see more agencies ask for real world testing. What does that mean? Go to a training center where we can put real Jet A on the ground with real props, like the three-dimensional prop you saw, pit props, aircraft props. Let's get it in vehicles and let's do real world live fire attack. And let's do it when it's pouring down rain. Let's do it when it's 30 or 40 knot winds that are gusting, perpendicular to the angle of attack. Let's do it in the real world and see what real world effects we can get. Um, but again, it's approved right now. You can put it on your rigs, keep your primary agent on board as required. But remember that most of us in the ARF world recognize the fact that, and thankfully, because I fly a lot, most of us will never go to a wide body down on fire on your airport. Thank God, right? Most of you will. But what do you go to every day? You go to car fires in the parking garage. You go to grass fires around the perimeter fence. You go to structure fires on your airport. You have fuel spills. You have other hazards where this is an ideal agent to have. So, it's something that consider having it because, 99% of your incidents, again, thank God, don't involve burning airplanes crumpled up on the end of the runway. Um, so again, we're coming up on 9:53 my time. I'm in outside of Portland, Oregon here. I thank you to all of you that are attending this in the middle of the night where you are. Thank you for all of you who have taken time out of your busy day. Thank you for all of you that are here because your minds are open and you'd like to look at maybe a better way of doing things, or at least another way of doing things. And hopefully, we've opened your eyes to wanting more testing, to having us come out and do live fire with you. We will do as much live fire as you want. I love to put my bunker gear and air pack on and set giant fires and put it out with F500. So please reach out to us. We would be very happy to work with you and worldwide. All right. Heather, I think we're good.
I see there's a few questions left in the Q&A. Did we answer those live?
All right, let me see. I'm going to kind of roll back through it and just double check. Are there new approaches in dealing with the upcoming technology in the aviation industry? Yeah, so no, we're leading the charge here, folks. That's the crazy thing is um much like, so look, the first production Tesla hit the road available for sale in 2003. It's 23 years later, and the fire service still doesn't have a consensus on how to deal with electric vehicle fires. So when it comes to eVTOL aircraft or hydrogen fuel cell powered aircraft, boy, we're behind the power curve. So we need to get out there. Again, we need to do more testing. We need to do more research. We need to get we need to get an Archer Midnight and take it to a training center and set the thing on fire. Those are things that we need to do. We need to work with industry to develop um, consensus standards, you know. Foams have to be on the Department of War QPL. Yes, to be used as a primary agent. They do have to meet that requirement. I will say, I will say, um, if you have to work with salt water, there is a reason why the U.S. Navy still uses AFFF because none of the approved mil-spec agents can be mixed with salt water, where F500 can be used with fresh, brackish, and salt water. So ideally, people talk about how do we, get this into more widespread use. Ultimately, what we would like to see is a encapsulator agent standard in the Department of War and an encapsulator agent standard in the FAA, much like there is for foam. And again, more real world testing. But yes, you cannot replace your primary agent with this right now, but you can carry it as a complementary agent. And let me tell you something, it will kill a jet engine nacelle fire in a blink of it. It is literally amazing how well it works. So um, again, so that those are things that we're working through. But I appreciate everybody being here. Appreciate taking the time to listen. We're coming right up on an hour, and have a great day. Please reach out to us if you have a question.